this DeBacco University video, I'm going to be going over the steps required for calculating net energy change of a reaction. While it may change here as we're going through chemical reaction, as bonds are altering and changing, we're going to be looking at the bonds forming versus those bonds breaking and the summaries of those. All right, so how is it calculated using bond enthalpies? Well, if you know the bond enthalpies of all bonds broken and formed, essentially what we're looking at is the change in enthalpy, as this uppercase sigma means summation of the bond energies of broken bonds subtracted from the summation of bond energies of bonds formed will get you your total bond energy. So those breaking bonds equals the energy absorbed or the input in an endothermic reaction, and the formation of bonds is the energy released or the output, and that'd be an exothermic portion to the reaction. Higher bond energy is simply equals a stronger bond. So the heat of a reaction tells you the net energy flow for the entire process. We'll go through a quick example here, hopefully it'll make a little bit more sense. So when we're looking at net energy change, to calculate that total net energy change of a chemical reaction, you're essentially figuring out how much energy is absorbed or released when bonds are broken and formed. So again, it's going to be this changing of molecules, this breaking of bonds, this forming of bonds. So energy is released when a bond forms, and energy is absorbed when a bond breaks. So we have this forming of bonds and this breaking of bonds. So in our little diagram here, releasing energy, we see a drop. That's going to be when a bond forms, and then energy is absorbed when bond breaks, and that's going to increase the bond energy here. So we can see how this changes as these chemical reactions are occurring. So the formula for a net change in delta H, which is enthalpy, again, the summation of bond energies broken minus the summation of bond energies formed. Breaking bonds requires energy, so it's going to have positive values, and forming bonds is going to release energy, and that will have negative values. So again, that requiring energy, breaking of bonds, positive values versus our negative. Here's an example of our endo and our exothermic reactions. Looking here, energy being released or energy being absorbed. So when we're releasing that energy, again, that's going to be our exothermic, because we're going to have less negative values. Here we're going to have energy absorbed. That's going to be breaking those bonds because that requires energy. So general step-by-step guide here. Again, I give you a lot of numbers over here on this side, but you want to start with writing a balanced chemical equation when you're going through and going to figure this out. Make sure all the reactants and products are accounted for on both sides of the equation here. I want to make sure you have a full, complete, and accurate equation that is also balanced. List all the bonds broken and the reactants. Count how many of each type of bond is broken. So when we're kind of looking at here, this kind of stepwise example, seeing bonds being broken, this is our reactant side, this will be our product side. You will have to likely go to one of these charts here to look at the energies, and then you want to account for how many of each type of bond you have. You want to list all the bonds also formed in the products. You want to count how many of each type of bond you have there as well. So again, here we've got 6, and here we've got 8 bonds here. If we count them all up, multiplying by that given number, getting our total number. We're going to use average bond energies. These are typically found in tables, as we can see located down at the bottom there. Those would be provided or given to you. You would use the average bond energies. These are typically found in tables, as you can see provided here, and you plug them into the formula. You add up the energy for all bonds broken and subtract the energy for all bonds formed. So you got this kind of accounting for the broken bonds as well as the formation bonds. So you're getting kind of that summation or that total change, that delta H or that total change in enthalpy of the equation. And we can see a great breaking down example right step by step here given, and you can see the end result. In this case, it is a negative number, important to keep track of. So we're looking at the combustion of methane just as an example. CH4 plus 2 oxygen molecules produces 1 carbon dioxide and 2 water molecules. So for our bonds broken, see our carbon and hydrogen bonds will be 4 of those, 2 oxygen bonds broken. We have the data provided from a table. Again, you can get one like the one provided right here. Then look at the bonds formed. So now we're on the formation of bonds. It's going to be on the kind of the product side. We have the carbon and oxygen bonds. We've got the oxygen and hydrogen bonds. We've got 2 of those and 4 of those. So we take those numbers that we have there. So if we look at the first one, 413 kilojoules per mole, we've got 4 of them. So 413 times 4. We have to add it to the 2 oxygen bonds here at 495. You can see that here. We have to subtract it from 2 times 799 because those are accounting for the bonds formed, and 4 times 463. We simplify those, and here's our numbers. We simplify those another step. We then go through the proper subtraction steps, keeping track of our signs, and we get negative 808 kilojoules per mole. With that number, we can have this summary that this reaction is exothermic, be giving off energy, and it's going to be releasing not just energy, it's going to be releasing 808 kilojoules per mole of energy. So again, with this information, writing that balanced equation, being able to know what sides to reactants to products, accounting for all those bonds, plugging in the numbers, you can therefore calculate or determine whether the reaction is endo or exothermic and exactly how much energy will be released or absorbed as a result of the reaction.